to find a hash that starts with 4 zeros.
Whenever a node mines a block, they get paid a little bit of that gas we were talking about earlier for doing so. A block in a blockchain is basically a combination of a block, nonce, transaction, and a previous hash to create this unique hash for this block. And again, depending on the blockchain implementation, this might have a couple other fields or might have different fields, but this is essentially what's going on. Blockchains are decentralized and distributed because many independent users are going to run this blockchain software, and it will check and they will compare against each other to see which blockchains are acting honestly and which ones are acting maliciously. In the blockchain world, majority rules. The nonce here is the answer used or the number used to get this hash. Now, nonce is kind of an overloaded term. It's actually used for a number of different reasons. In this case, we're using it to solve this problem of getting 4 or 5 zeros at the stop of the hash. However, in Ethereum, it'll also be often used as the number of transactions from a given address. So now we're going to talk a little bit about signing these transactions and private keys and some other cryptography pieces, right? Because in this blockchain demo here, we can see we have all these fantastic transactions, right? All these things went through, but how do we know that it was Darcy who was the one to send $25 to Bingley, right? How do we know that actually happened? And this is where all those pieces that we just learned about in our testnet, in our MetaMask account, are really going to start to come to life here a little bit here. So here we have an example of public and private keys. Okay, at the top we have this private key, right? That was randomly generated. A private key is as it kind of states, is a key that you really want to keep secret because you're going to be using this as kind of your secret password for all your transactions, right? I can really pick any private key, anything that I want, and with it, this algorithm, they're going to use an algorithm. For Ethereum and Bitcoin, they both use this elliptic curve digital signature algorithm. It's a variant of just a digital signature algorithm, and it's going to create this public key, right? I'm really not going to go at all into kind of this digital signature algorithm, but just know it does use some of these some of the hash knowledge that we just learned, combined with some other pieces. To kind of get this public key here. So I'm not going to go too deep into it, but we have this private key that we create and we get this public key. Now this public key, we want everybody to have access to, right? This is, whole world can see this private key. We really want it to be private. We don't want people to see this. We're going to use this private key as like a password to quote unquote digitally sign transactions. And then people can verify them with this public key. So let's see what this actually looks like. Let's pick a random key, a more secure key, right? Because the longer it is, the more secure it's going to be. And if we go to signatures now, right? Let's say we have this this message that we want, right? We'd say hi world, right? We want this to be the message. What's going to happen is this private key that we've created, we can use to sign this data, right? Remember how in the blockchain demo, we were hashing stuff, right? We're using this SHA-256 hash to get this hash. Well, we're doing something similar, but instead of hashing, we're using this digital signature algorithm to create this message signature. Now, what's really powerful about how this algorithm works is that you can create this message signature with your private key, but somebody else can't derive your private key from the message signature. And that's what makes this really, really powerful. However, if we go to verify using this public key, right? And so this is that 0403. This is that same public key. Using this public key, anybody can verify. Oh, let's go ahead and sign it again. Anybody can verify that this signature is yours, right? So you have a private key just for you, so you can sign things, and a public key so that anybody can verify something, right? So anybody can verify this, and let's say somebody tries to fake a transaction from you. They say, "Hey, this is their transaction." All they have to do is verify that this signature against your public key, and very easily this whole thing turns red because it isn't verified, right? The algorithm says, "Hey, that's wrong." So we can go ahead and take that into transactions in this exact same way. So if I want to send money, if I want to send $400 from, my address to another address, using my private key, I can sign that transaction. And anybody else in the world can then verify this transaction, right? And this is why when people say, hide your keys, protect your keys, this is what we're talking about. in our accounts here, right? If we go to settings, and again, the only reason that I'm showing you guys my mnemonic and my private key is because this is a dumpster account. I'm going to throw this away at the end of this video, or I'm just not going to put any real money in it. But when we look at our MetaMask here, we have this mnemonic phrase, which allows us to easily get these different private keys, right? So mnemonic phrase combined with, whatever account number will get us a private key. So mnemonic phrase combined with 1, we're going to get this private key. And this is when we look at account details, export private key, password confirm. This is going to be the private key that we're going to use to sign our transactions, right? This, if anybody else gets access to this private key, they then can sign transactions for us, and they can send transactions for us. And that's why we want to keep these private. So it works the exact same way, right? And so this is why it's so important to hide your private keys and hide your mnemonics. Now, your Ethereum address is actually a piece of your public key. Now, to get our address in Ethereum, all we have to do is take this public key that we've created with our private key, hash it using that same Ethereum hashing algorithm, and then take the last 20 bytes. And that's how we'll actually derive to our address here. Now, knowing the exact methodology of how to get the address doesn't really matter because it could change blockchain to blockchain and could even change in ETH2. But just know that that is essentially how kind of these addresses are derived, right? There's some derivative of the public key, right? Because the public key is public, and using the public key in kind of any public way is totally fine, but not the private key. So that is how we sign our transactions. Note though, this isn't how we send the transactions. So this is just going to sign it, create a transaction for us to send. We'll learn later on how to send these transactions. Whew, so that was a lot of information there too. Let's do a quick recap. Your public key is derived by using a digital signature algorithm on your private key, right? And you want to keep your private key private at all times because you're going to use your private key to sign transactions. Signing transactions with your private key, you are the only one who can actually do this because you can't get the private key from a message signature. However, using your public key, anybody can very easily verify that a signature that's signed by you is in fact signed by you. In our MetaMask, our private keys are located in this account details section. You just hit show private keys and type in your password, and you'll get your private key here. A quick note here is oftentimes when using your private key somewhere, they want it in hexadecimal form. So if we're going to use our private key for something like Brownie, which we'll go into later, we need to actually append a 0x to the front, but we'll get into that later. And the address of your account is derived from this. So if you think about it, your private key creates your public key, which then can create your address. And there's a little barrier here, or a big barrier here, because your private key you want to keep private, and your public key and your address can all be public information.
Awesome. So now that we know all the cryptography pieces and all the little nitty-gritties of how the blockchain actually works and how our signatures work and how everything sticks together, let's talk a little bit about how this works in actuality and what's really going on. Now, for a lot of this, each different blockchain has slightly different algorithms and slightly different metrics and criteria for doing a lot of this stuff. So when we're talking about these specific implementations, keep in mind the exact algorithm might be a little bit different, but the concepts are all still going to be exactly the same. Hashing and a hash function is going to be the same no matter where you look. A decentralized blockchain is going to be the same no matter where you look. How it's actually implemented is going to be a little bit different. Now, traditionally, when you run an application, be it a website or something that connects to some server, you are interacting with a centralized entity. And unlike how we saw with the blockchain with multiple different peers, it's going to be run by a single centralized group. Now, it still could be run on many different servers, but all those servers are still going to be controlled by the same centralized group. Blockchains, as we saw, run on a network of different independent nodes. When we saw peer A, peer B, peer C, those were different examples of different independent users running the blockchain technology on their own node. Now, when I use the term node, I'm usually referring to a single instance of a decentralized system. So when I say a single node, when I'm talking about a blockchain, I'm talking about one of those peer A's, peer B's, peer C's running that blockchain software. I'm talking about one server running this technology. And again, it's this network, it's this combination of these nodes interacting with each other that creates this entire blockchain. What makes these so potent too is that anybody can join the network, and that's why there's decentralized. The barrier to entry is a little bit of hardware requirements, you getting the correct materials to run the software, and then you running the software. Anybody can join these networks and participate, and that's what makes it truly decentralized. In fact, you can go to GitHub right now and run your own Ethereum node in a few seconds. Now, in the traditional world, applications are run by centralized entities, and if that entity goes down, or is maliciously bribed, or decides that they want to shut off, they just can't, because they're the ones that control everything. Blockchains, by contrast, don't have this problem. If one node or one entity that runs several nodes goes down, since there are so many other independent nodes running that it doesn't matter. The blockchain and the system will persist so long as there is at least one node always running. And luckily for us, most of the most popular chains like Bitcoin and Ethereum have thousands and thousands of nodes. And as we showed in our demo, if one node acts maliciously, all the other nodes will ignore that node and kick that out or even punish it in some systems, because they can easily check everybody else's node and see, okay, this one is out of sync with the majority. And yes, majority rules when it comes to the blockchain. Each blockchain keeps a full list of every transaction and interaction that's happened on that blockchain. And we saw if a node tries to act maliciously, then all their hashes are going to be way out of whack and they're not going to match everybody else. This gives blockchains this incredibly potent immutability trait where nothing can be changed or corrupted. So in essence, we can think of a blockchain as a decentralized database. And with Ethereum, it has an extra additional feature where it also can do computation in a decentralized manner. Now let's talk consensus, proof of work, and proof of stake, because you've probably heard these before and they're really important to how these blockchains actually work. When we went through that blockchain example and we did that mining feature, this is what's known as proof of work. Proof of work and proof of stake fall under this umbrella of consensus. And consensus is a really important topic when it comes to blockchains. Consensus is defined as the mechanism used to reach an agreement on the state or a single value on the blockchain, especially in a decentralized system. I briefly alluded to this consensus mechanism in our blockchain example when I said if one changes something and the other two don't, then majority will rule and kick that one out. This is part of that consensus mechanism. Now, very roughly, a consensus protocol in a blockchain or decentralized system can be broken down into two pieces: a chain selection algorithm and a Sybil resistance mechanism. That mining piece that we were doing, or the proof of work algorithm, is what's known as a Sybil resistance mechanism. And this is what Ethereum and Bitcoin currently use. Please note that depending on when you're watching this, if ETH2 is out, then it's no longer proof of work. Now, proof of work is known as a Sybil resistance mechanism because it defines a way to figure out who is the block author. Which node is going to be the node who did the work to find that mine and be the author of that block, so all the other nodes can verify that it's accurate. Sybil resistance is a blockchain's ability to defend against users creating a large number of pseudo-anonymous identities to gain a disproportionately advantageous influence over said system. And in layman's terms, it's basically a way for a blockchain to defend against somebody making a bunch of fake blockchains so that they can get more and more rewards. Now, there are two types of the Sybil resistance mechanisms that we're going to talk about here, namely proof of work and proof of stake. Let's talk about proof of work a little bit more in depth first. In proof of work, this is Sybil resistant because a single node has to go through a very computationally expensive process called mining, which we demonstrated earlier, to figure out the answer to the blockchain's riddle of finding that correct nonce or whatever the blockchain system has in place. In proof of work, this works because no matter how many pseudo-anonymous accounts you make, each one still has to undergo this very computationally expensive activity of finding the answer to the proof of work problem or the proof of work riddle, which again, in our demonstration, it was finding a nonce with that first 4 zeros. But again, each blockchain might change the riddle or change the problem to be a little bit different. In fact, some of these blockchains make this riddle intentionally hard or intentionally easy to change what's called the block time. The block time is how long it takes between blocks being published, and it's proportional to how hard these algorithms are. So these problems actually can change depending on how long they want the block time to be. If a system wants the block time to be very, very long, they just make the problem very, very hard. If they want it to be very short, they make the problem a lot easier. We'll talk about Sybil attacks in a little bit and how they can affect the system. But with proof of work, it's a verifiable way to figure out who the block author is and be Sybil resistant. Now, you need to combine this with a chain selection rule, create this consensus. Now, there's some consensus protocols that have more features, but very, very roughly, these are the two pieces that we're going to look at. The second piece is going to be a chain selection rule. How do we know which blockchain is actually the real blockchain and the true blockchain? Now, on Bitcoin and Ethereum, they both use a form of consensus called Nakamoto consensus. And this is a combination of proof of work and longest chain rule. The decentralized network decides that whichever blockchain has the longest chain or the most number of blocks on it is going to be the chain that they use. This makes a lot of sense because every additional block that a chain is behind, it's going to take more and more computation for it to come up. That's why when we saw in our transaction, we actually saw confirmations. The number of confirmations is the number of additional blocks added on after our transaction went through in a block. So if we see confirmations as 2, it means that the block that our transaction was in has 2 blocks ahead of it in the longest chain. Now, I do want to point out that a lot of people use proof of work as a consensus protocol, and I do want to say that this is a little bit inaccurate, but sometimes people use it interchangeably. Proof of work is a piece of the overall consensus protocol, which in Bitcoin and Ethereum 1's current case is Nakamoto consensus. Nakamoto consensus is a combination of proof of work and this longest chain rule, both equally and very, very important. Now, proof of work also tells us where these transaction fees and these block rewards go to. Remember how when we made this transaction, we had to talk about gas and a transaction fee. So who's getting paid? Who is getting this transaction? And this transaction fee is going to the miners or the validators. In a proof of work network, they're called miners, and in the proof of stake network, they're called validators. They are a little bit different, and we'll get into that when we talk about proof of stake. In this proof of work system, all these nodes are competing against each other to find the answer to the blockchain riddle. Remember, in our example, it was to find a hash that has 4 zeros at the start. And again, depending on the blockchain implementation, that riddle is going to be a little bit different. But all the nodes are trying as many as possible to try to get this answer first. Why? Because the first node to figure out the answer to the blockchain riddle is going to get that transaction fee. They're going to get paid from that. Now, when a node gets paid, they actually get paid in 2 different ways. One is going to be with a transaction fee, and another piece is going to be the block reward. Remember how we talked about alternating the gas price or the GUI on our transaction? Well, that's the transaction fee that we're going to pay to these blockchain nodes for including our transaction. The block reward is given to these nodes from the protocol, from the blockchain itself. You've probably heard of the Bitcoin halving before. The halving is referring to this block reward getting cut in half, and it's supposed to be cut in half roughly every 4 years. This block reward increases the circulating amount of whatever cryptocurrency that is being rewarded. For example, on Ethereum, the block reward is giving out Ethereum, and on Bitcoin, the block reward is giving out Bitcoin. So these nodes are competing against each other to be the first one to find this transaction, to be the first one to find the answer to this problem, so that they can be the ones to win both this block reward and your transaction fee. Some blockchains, like Bitcoin for example, have a set time when they're no longer going to give out block rewards, and the miners or the nodes are only going to get paid from transaction fees. Now, this gas fee, again, is paid by whoever initialized the transaction. When we got our funds from the faucet, there was some server and somebody else was paying the transaction fee for us. However, when we sent Ether from one account to another, our first account actually paid some transaction fee to send that Ether. In proof of stake, there's also a gas fee, but it's paid out to validators instead of miners, and we'll talk about that in a little bit. Now let's talk about 2 types of attacks that can happen in these blockchain worlds. Let's talk about the first one being the Sybil attack. The Sybil attack is when a user creates a whole bunch of pseudo-anonymous accounts to try to influence a network. Now, obviously, on Bitcoin and Ethereum, this is really, really difficult because the user needs to do all this work in proof of work or have a ton of collateral in proof of stake, which again, we'll talk about in a bit. The other more prevalent attack is what's known as a 51% attack. Now, as we saw as part of our consensus protocol, these blockchains are going to agree that the longest chain is the one that they're going to go with, so long as it matches up with 51% of the rest of the network. This means that if you have the longest chain and you have more than 51% of the rest of the network, you can do what's called a fork in the network and bring the network onto your now longest chain. Now, Sybil attacks obviously are when a single node or a single entity tries to affect the decentrality of the network by pretending to be multiple different people, although they're just the same person or entity. And like I said, it's really difficult to do in proof of work and proof of stake. So you can see now that blockchains are very democratic. Whichever blockchain has the most buy-in and is the longest is the blockchain that the whole system is going to corroborate. When nodes produce a new block and add it to the longest chain, the other nodes will follow this longest chain that the rest of the network is agreeing with, add those blocks to their chain, and follow up. So very small reorganizations are actually pretty common when a blockchain picks a block from a different longest chain, puts it on, and then has to swap it out for another block and continue with a different blockchain. However, if a group of nodes had enough nodes or enough power, they could essentially be 51% of the network and influence the network in whatever direction that they wanted. This is what's known as a 51% attack, and it's happened on blockchains like Ethereum Classic, which is not Ethereum. This is why the bigger a blockchain is, the more decentralized and the more secure it becomes. So after you watch this video and you become a blockchain engineering expert, I definitely recommend you run a node as well, because you are going to increase the security of the network as a whole by running a node. So proof of work is fantastic because it allows us to very easily protect against these Sybil attacks and keep our blockchains decentralized and secure. However, it has some drawbacks as well. Proof of work costs a lot of electricity because every single node is running as fast as they can to win this race to get the rewards. This leads to, obviously, an environmental impact. Now, since proof of work and Nakamoto consensus, a lot of other protocols have taken this idea and gone in a different direction with a different Sybil resistance protocol. A lot of them with the intention to be a lot more environmentally friendly. And the most popular one right now is proof of stake. There are some chains that are already using this proof of stake protocol and that are live and thriving. Some of them are like Avalanche Solana, Polygon, Polkadot, and Terra. And additionally, Ethereum has decided to upgrade to ETH2, which will have this proof of stake algorithm as well. It'll also have some other features which we'll talk about in a bit. Now, as a quick aside, all the tools that we're going to learn here are still going to work in ETH2. So depending on when you watch this, everything here is still valid. So let's talk about proof of stake now. Again, this is a different Sybil resistance mechanism. Instead of solving this difficult problem, proof of stake nodes put up some collateral that they're going to behave honestly, aka they stake. In the example of Ethereum 2, nodes put up some Ethereum as a stake that they're going to behave honestly in the network. If they misbehave in the network, they are going to be slashed or removed some of their stake. Obviously, this is a very good Sybil resistance mechanism because if you try to create a whole bunch of anonymous accounts, then each one of those accounts, you have to put up some stake. And if you misbehave, you're going to run the risk of losing all the money that you put up as collateral. In this system, miners are actually called validators because they're no longer mining anything. They're actually just validating other nodes. Now, unlike proof of work, which every node is racing to be the first one to find the block, in proof of stake, nodes are actually randomly chosen to propose the new block. And then the rest of the validators will validate if that node has proposed the block honestly. As we saw with our cryptography lesson, it's usually very easy for other nodes to verify if a proposal or a transaction is honest. Now, randomness is a really important topic when we're talking about blockchains, because keep in mind, these blockchains are deterministic systems. They're walled gardens from the rest of the world. And as you know, a deterministic system, by definition, can't have random numbers. So how do we choose the random validators in the system? Well, it changes from blockchain to blockchain, and actually choosing the node will change blockchain to blockchain. But in ETH2, they're using what's called RANDAO, at least for the original implementation. This is a decentralized autonomous organization that collectively chooses the random number and collectively chooses which node is going to run next. We aren't going to dive too deep into this because there's a good chance that this might change in the future. But we will go into randomness solutions in blockchain later on in this course. Now, proof of stake obviously has some pros and cons as well. Pros are that, again, it is a great Sybil resistance mechanism and a great way to figure out who the author of a block should be. The other pros are that it's way less computationally expensive to figure out the new block, because instead of every single node on the network trying to do this, only one node needs to do this. And then the rest of the nodes just need to validate it. The cons are that it's usually considered a slightly less decentralized network due to the upfront staking costs it costs to participate. Now, this gets into a little bit of a philosophical battle on how decentralized is decentralized enough, and I think that's up to the community to decide. And as we progress, I think we'll learn more and more about how decentralized is decentralized enough. The general consensus amongst blockchain engineers, though, is that proof of stake is very, very decentralized and very secure. This massive environmental impact improvement is one of the two main reasons why ETH is shifting to ETH2. It reduces the environmental impact by up to 99%. Now, these are the main pieces of proof of work and proof of stake, but I did want to talk about another concept that's really important in these ecosystems, and that is scalability. When we were talking about gas prices, we were saying that the gas prices can get really high if a lot of people want to send a transaction, because a block only has so much block space and the nodes can only add so many nodes. So when a lot of people want to use a blockchain, the gas price skyrockets. This is not very scalable, because if we want to add more and more people to these blockchains, it's going to cost more and more to use the blockchains because more people are going to want to get into these blocks. This means that there's kind of a ceiling to how many people can use the system because of the financial constraints that'll get imposed as gas prices keep rising. Ethereum 2 is not only attacking the environmental impact of proof of work by switching to proof of stake, but they are also implementing this new methodology called sharding. And sharding is a solution to this scalability problem. A sharded blockchain really just means that it's going to be a blockchain of blockchains. There is a main chain that's going to coordinate everything amongst several chains that hook into this main chain. This means that there's more chains for people to make transactions on, effectively increasing the amount of block space that there is. Sharding can greatly increase the number of transactions on a blockchain layer 1. Now, there's another term that might be the first time you heard it, a layer 1. We're going to talk about layer 1s and layer 2s in terms of scalability really quickly as well. A layer 1 refers to any base layer blockchain implementation. Bitcoin's a layer 1, Ethereum's a layer 1, Avalanche is a layer 1. These are the base layer blockchain solutions. A layer 2 is any application that is added on top of a layer 1, added on top of a blockchain. Some examples of layer 2s are going to be Chainlink, Arbitrum, or Optimism. Arbitrum and Optimism are very interesting because they are layer 2s that also look to solve this scalability issue. Arbitrum and Optimism are what's known as rollups, and they roll up their transactions into a layer 1, like Ethereum. We're not going to go too deep into rollups and how they actually work, but all you really need to know is that a rollup is kind of like a sharded chain. They derive their security from the base layer, from the layer 1, like Ethereum, and they bulk send their transactions onto the layer 1. They solve some of the scalability issues by being another blockchain that people can make transactions on, still on kind of this base Ethereum layer. Now, they're different from side chains because side chains derive their security from their own protocols. Rollups derive their security from the base layers. So Arbitrum and Optimism, for example, is going to be just about as secure as Ethereum. There's some fantastic guides in there that go a little bit deeper into rollups, and I've left a link in the description for you. All right, so we just talked about a lot of stuff. So let's do a quick recap before moving on. Ethereum and Bitcoin are currently both proof of work blockchains that follow Nakamoto consensus. However, Ethereum is moving to Ethereum 2, which will be a proof of stake sharded blockchain. Sybil attacks are prevented due to protocols like proof of work and proof of stake. 51% attacks grow increasingly harder with the size of blockchain, so you should run a node. Consensus is the mechanism that allows a blockchain to agree upon what the state of the blockchain is. Sharding and rollups are solutions to scalability issues on layer 1s. A layer 1 is any base blockchain implementation, like Bitcoin or Ethereum. A blockchain scalability problem is that there's not always enough block space for the amount of transactions that want to get in them. This leads to very high gas prices. And again, gas prices are how much it costs to interact with a blockchain. Whew. So we've learned a ton in this video so far. Everything that you went over is going to make you 10 times better as a developer. Because yes, being a good developer means you understand the code at a very technical level. But if you can understand the overall architecture as well, you can make informed decisions about how to architect your design or how to build your software in however you want to do so. So with all that being said, it's finally time to jump into some Solidity and jump into some code. So let's do this.
Now again, in the description of this video, there is a link to this GitHub repository. That's going to be the home base for all the code that we work with in this tutorial. We scroll down to this main section, this README, there's a table of contents in here. We can go to Lesson 1, Simple Storage, and we'll have links, helpful tips, the itinerary of what we're going to learn, and everything else that you need to work with here. All the code that we're going to be working with is located in this Simple Storage link that we can go ahead and click. It's in its own different repository. We can go ahead and click the file to see all the code that we're going to be working with. So let's jump into it. Additionally, back in our full blockchain Solidity course, right at the top, there's this resources for this course section. If you have questions, engaging in GitHub discussions, Stack Exchange Ethereum, and Stack Overflow are going to be great places to get help and get support. I highly recommend making a Stack Overflow, Stack Exchange Ethereum, and a GitHub account so you can participate and engage with the community. Welcome to the Remix IDE, or the Remix Integrated Development Environment. This is going to be where we're starting to teach you how to work with Solidity and work with smart contracts and deploy to blockchains. We're going to use Remix to get us up to speed, as it has a lot of nice features that allow us to really see and interact with blockchains and really see what's going on. But eventually, we're actually going to move off of Remix to another platform. But all the Solidity that we're going to learn here obviously is going to apply everywhere as well. When you come to Remix, there's a whole lot of different plugins like Solidity, Learn ETH, Sol Hint Linter, and a whole bunch of other plugins as well. I'm going to go ahead and start by clicking the Solidity plugin, but we're not going to use any of these plugins for now, but later on you can kind of go back and learn a little bit more about what these plugins do. So let's start perusing. Let's start coding some things. On the left-hand side over here is where we're going to interact with everything. So let's go ahead and click the files up here. Now you can always go back and peruse this a little bit more. And in fact, I highly encourage you to, because that's how you're going to learn the most, the quickest. But for us, we're actually just going to go ahead and start with our own brand new file. We're going to create a little application that can store information on the blockchain for us. And this is our first project that we're going to do in Solidity. So we're actually going to create a new file, and we're going to call it simple storage.sol. All Solidity has an extension of .sol at the end. It stands for Solidity. Now let's take inventory of what we're going to be working with here. This is the Solidity compiler tab. It compiles all the Solidity code down to machine understandable code, or machine language here. There's a whole bunch of different parameters we can choose when working with Solidity. We can choose the compiler version, we can choose the language, which we're only going to be working with Solidity, the EVM version, don't worry about this for now. So let's code our first Solidity contract here. Now we are going to use something a little bit special here. When we actually deploy these, we're going to use a JavaScript virtual machine. So we're going to use a virtual machine that's going to simulate actually deploying to a testnet or a real network. We're not actually going to deploy on a real network. We will in a little bit. But just to get started, we're going to work with a JavaScript VM, which is kind of a fake environment for now, okay? Testing locally and understanding how to test locally will make your coding experience a lot faster. As you saw, when we sent some transactions, some of them actually took a lot of time to actually deploy. We don't want to have to spend that much time waiting around for our tests to actually finish. So we're going to use a JavaScript VM to kind of dummy it for now. But let's just start coding and go from there. So the first thing that you're going to need in any Solidity program is the Solidity version. So that's always going to be at the top of your Solidity code. It's defined by doing pragma, Solidity, and the version. We're going to be using some version between 0.6.0 and 0.9.0. So we're saying we want to use anything between 0.6 and 0.9. And as a force of habit, I just automatically hit Command S whenever I write anything. So that's why you saw some of this pop up here. Hitting Command S or Control S, depending on if you're Windows or not, we'll hit this compile button and we'll compile everything for us. Now, if we want a specific version of Solidity, we can also do 0.6.0. And if I go ahead and hit Command S or compile, our compiler will automatically revert to 0.6.0. However, if I try to do 0.8.0 with my Solidity at 0.6.0, it's going to give us an error. It's going to say the source file requires a different compiler version. We're using 0.8.0 and this is 0.6.0. So we're going to go ahead and hit compile and it's going to automatically move down to 0.6.0. We can also do caret 0.6.0, and this will allow us to work with really any version of 0.6. It'll work all the way up to 0.7, where if we hit Command S or Control S there, it'll give us an error. So this only works with any version
below 0.7 and above 0.6. we're going to be using version 0.6.6.
However, in future contracts that we work with, we're actually going to work with different versions of Solidity. The reason we're going to be changing versions throughout this course is that Solidity is a constantly updating language.
Being good at switching between versions is going to make you an incredibly powerful smart contract engineer.
The next thing that we're going to do is we're going to define our contract. So contract is a key word in Solidity, which stands for our smart contract that we're going to create. You can think of a contract similar to a class in Java or any other object-oriented programming language. So we're going to give our contract a name here. We're going to call it simple storage. And we're going to add this little curly bracket to say this is the contents of our contract simple storage. And I went ahead and hit Command S, and we can see it is compiling successfully. You could hypothetically deploy this right now, and this would be a valid contract. So great job for making it this far. Now in Solidity, there are many different types that we can work with. Let's go into some of the types of Solidity. We can have integers, aka whole numbers. They can be uint, as in an unsigned integer, meaning they're not positive or negative. We can also have an int, and we would define a variable by doing uint 256 favorite number equals 5. So we have an unsigned integer. Uint 256 means this is an integer of size 256 bits. So we can have this number be up to 256. You can also do uint favorite number equals 5, but if you want to be a little bit more precise, a lot of protocols and a lot of smart contracts will do the whole name like uint 256. We can also have booleans. Booleans are true, false. So we can have boolean favorite bool equals true. So this favorite bool would be true. It could also be false. We can have strings. String favorite string equals string. A string is a string of text here, right? It's going to be some word or phrase or really any of these keystrokes here. Similar to the unsigned integer, we can have an int 256. Favorite int equals -5. So it could be positive or negative. We can have an address, which is going to be some type of Ethereum address. So we could do address, favorite address equals, and then we can even copy right from our MetaMask and just paste it right in here. This is going to be a valid address here. You'll also notice that we end all of our statements with a semicolon. We can have a bytes object, size 32 bits, favorite bytes. For our example, we're just going to use the word cat because cat is a string which can be converted down into a bytes object. Byte 32 means that there's 32 bytes in this variable favorite bytes. We can also do bytes 2, bytes 3, bytes 5, etc. with a maximum size of bytes 32. For example, we can't do bytes 64. We're going to be talking about some other variables as well, like arrays and mappings, but let's just stick here for now. If you want to learn more about the different types and the different variables that you can use, head over to the Solidity documentation, and there's a link in the GitHub and the description to show you this section. For now, for our simple storage, let's say we only want to store numbers. We don't want to store anything else. So we're just going to go ahead and delete everything and just have uint 256 favorite number at the top. Now in Solidity, if I do this, favorite number actually does get initialized even though I didn't have it initialized to 5. If I leave it blank, it gets initialized to the null value. In this case, it would be initialized to 0. So for now, let's just not initialize it to anything. That way it'll get automatically initialized to 0. This means that when we deploy this contract, as of right now, favorite number will start off as 0. If you get confused, you can also make a comment on this. You could say, this will get initialized to 0. This double slash here is the way to make comments in Solidity, and it won't get executed as code. So we can write whatever we want as long as it's preceded by 2 backslashes. Now let's go ahead and create our first function. Functions or methods are self-contained modules that will execute some task for us. And in Solidity, it's the exact same thing. They're defined by the keyword function. let's make a function called store that will change the value of this favorite number here. So we're going to call store, and we're going to allow it to be passed a variable. So we're going to allow it to be passed a variable of type unsigned integer 256, and we're going to call it underscore favorite number. We're going to make this a public function, which we'll get to in a minute. And all we're going to do is we're going to set favorite number equals to whatever variable we passed in, favorite number. So this, in its simplest form, is how you can define a function. Now, just to visualize what we're working on so far, let's go ahead and deploy this contract so we can actually start to interact with it. So if we hit this button, this will bring us to the Deploy tab and will allow us to deploy our smart contract here. Using our JavaScript VM, it's given us a fake account with some Ethereum in it. It has 100 Ethereum in it to start. And same as before, anytime we want to interact with the blockchain, we have to pay a little bit of gas, even in our fake virtual machine here. And we want to simulate that. So you'll see it has some of the same parameters here as making a transaction, like gas limit, for example. When we deploy a contract, it's going to cost a little bit of Ethereum or a little bit of gas to do so. So let's go ahead and hit this deploy button and see what happens. So once we deployed with this virtual machine, a few things happened. We have Remix kicking out this section down here saying, great job, you've deployed something. And if we scroll down, it says transactions recorded 1. We can look at all the transactions we recorded, and we can see it says deployed contracts, and we have a contract here that we've deployed. Now let's zoom out just a hair here so we can see everything a little bit better. In this simple storage contract, we see this big store button because there's one public function that we can actually interact with. So we can add this number here and we'll hit store, and you'll see again, we have a completed transaction. And if we look at our contract, we'll have paid a little bit more gas, right? We'll have paid a little bit more to interact with this function because again, anytime we want to make a state change on the blockchain, we have to pay a little bit of gas. The reason MetaMask isn't popping up is because we're kind of doing it in this simulated environment. So this is great. However, it looks like we can't actually see what our favorite number is. We can't actually look at it. So how do we actually make sure that we can view this favorite number? Well, let's add another parameter to this as well. If we add public to our favorite number, we recompile by hitting Command S or hit the compile button. We delete this contract and we redeploy and scroll down. Now we'll see two buttons pop up. This blue button to show us favorite number, which again is initialized to 0, and we have this store function. So let's talk a little bit about why this public variable allowed us to see this new button, this new favorite number button. This public keyword defines the visibility of the variable or the function. There are currently 4 different types of what's called visibility in Solidity. There's external, public, internal, and private. We're mostly going to be working with public for now, but it's important to note how the rest of these work. Public functions can be called by anybody, including variables. So oddly enough, variables are a function call to just look at them
and return whatever that variable is.
An external function means it can't be called by the same contract. It has to be called by an external contract. So if in this contract, I had this be external, I couldn't call the store function. I couldn't call the store function inside this function because the function is external. It means somebody outside of the contract has to call this function. Internal functions, however, can only be called by other functions inside of this contract or in its derived contract. And then private is the most restrictive, as private functions and state variables are only visible for the contract they are defined in and not derived contracts. Now, the reason that we didn't see favorite numbers show up in our original contract deployment is that if we don't give a state variable a visibility, it will automatically get set to internal. So if we want other people to be able to read it, we have to change it to public. Now, let's see how this interaction actually works. If we hit the favorite number button right now, we'll get this call thing that shows up, and it'll show us right here that the value of favorite number is 0. Now, this function, however, is set so that whatever value we pass it is going to change the favorite number to whatever we pass it as. So if we pass 1, 2, 3, hit store, that transaction goes through, and then hit favorite number, we can see the value is now 1, 2, 3. Now, I will also be using transactions and smart contract interactions and function calls a little bit interchangeably. That's because on a blockchain, whenever you call a function or whenever you make some state change to the blockchain, you're actually also making a transaction. That's what makes this whole thing so powerful. And again, that's why making a function call or deploying a contract costs a little bit of gas. Now, the reason we can access this favorite number variable inside this function is because favorite number has this global or contract scope. So even if we made uint256 test equals 4 or equals 4, we wouldn't be able to use this variable outside of this function, right? Because it's self-contained. It's self-contained inside this bracket. And if I were to make another function, store2 perhaps, public, store2 doesn't know that this test variable exists. Functions only know about the variables that are in the same scope as them. So favorite number is in this global scope because the only bracket that's above them is simple storage. And test is in this store scope because it has 2 brackets above it. It's inside of this store function and inside of this contract simple storage. Store2 isn't inside of this store function or this store scope, so it can't access this test variable. So let's go ahead and make this back to public, and we'll compile. Again, I'm hitting Command S to compile, but you can go ahead and click the button if you like. And let's get rid of this and get back. Now, as you saw, when we deploy this, there's this button here that we can click called favorite number. We can also make a function called retrieve and make it a public function that is of type view and returns uint256. And all this is going to do is return favorite number. So we're going to talk about views and returns here. So I'm going to go ahead and compile. I'm going to go ahead and delete this contract. I'm going to go ahead and deploy it now. And we can see now we have 2 functions or 2 blue buttons here. We have retrieve and we have favorite number. And if I change favorite number by calling the store function, favorite number and retrieve will both now say it's 1, 2, 3. So then the question might be, well, why is this one orange and these 2 are blue? And the key relies in this view function or this view keyword. There are 2 special keywords that define functions that you actually don't have to make a transaction on. And those keywords are view and pure. A view function means that we want to read some state off the blockchain. So we're just reading off the blockchain. If we're reading off the blockchain and we're not actually making a state change, then we don't need to make a transaction. These blue buttons are blue because they are view functions. Public variables also have view functions. That's why both of these are blue. This technically is a view function. And when I click it, I get to view and I get to read the state off the blockchain. Retrieve is the same way. We could have this without a return, but it wouldn't do anything. Pure functions are functions that purely do some type of math. We could have uint256, favorite number, public pure, and just have favorite number plus favorite number. So we're doing some type of math here, but we're not actually saving state anywhere. We're going to do this math, but we're not going to save this favorite number anywhere. We're not going to save anything. Deploy this now, this pure function. We would have this retrieve function, 1, 2, 3. It's blue as well because it's, again, not going to change the state of the blockchain. So view functions and pure functions are both going to have this blue color. Now, the reason that nothing shows up at the bottom is because we didn't return anything. All we're doing is we're saying, add these 2 numbers together, and that's it. In order for this function to give us something back, we need to have it return something. So if we go back to this retrieve function, we have to define what we're going to return when we're defining this function. So we're going to say this is a public function. It's a view function because we're going to read some state, and it's going to return a uint256. So favorite number is a uint256, so that's what we're going to return. Our public variable favorite name is also a view function that returns a uint256. For now, let's just remove that so we can work with this retrieve function. So let's go ahead and deploy. So now we see we don't have this favorite number button anymore because it is no longer a public function. Because again, it gets initialized to internal, so we can't actually view it. Now keep in mind, later on, we're going to talk about how everything on chain you actually can see, and we'll talk about that a little bit later though. So retrieve is going to do 0, we can call store, and now retrieve is going to be 1, 2, 3. Now this application is great so far. It allows a single person to store a favorite number and then go ahead and retrieve it later, which is fantastic. But what if we want a list of people or a group of people and store their favorite numbers? Or what if we want to associate a favorite number with a single person? Well, what can we actually do? Now we have a whole number of different choices, but the one that we're going to talk about is using a struct. Structs are ways to define new types in Solidity. They're almost like creating new objects as well. So we can create a struct called type people and allow it to start storing a favorite number associated with a certain people. So inside of our struct, we can have different types as well. So we can have a uint256 favorite number, and we could also have a string name. Now we have a new type of type people that has a favorite number and a name inside of it. Now what we could do with the struct is we could say people public person equals people, and then inside we add the variables. So we could say favorite number, favorite number is 2 and name is Patrick. And of course the semicolon at the end. And again, I'm hitting Command S to save, but you can also go ahead and compile in the compile tab. So let's go ahead, delete this contract, and see what this looks like now. So now we've deployed this new contract, and we have this person struct, which at the 0th index is the favorite number, and the variable stored in the first index is going to be the name. Storing variables in Solidity always works in this numeric index fashion. In fact, in contract simple storage, uint256 favorite number is at index 0. If we were to add another object here, like boolean favorite bool, this would be at index 1. If we were to add bool favorite bool 2, this would be at index 2. 0, 1, 2. And it works the same in structs. This is at index 0 inside the struct. This is at index 1 inside the struct. So we can see the variables associated with this person. We're going to go ahead and delete this for now, because instead of just creating one person, we actually want to create a whole list of people. So how do we create a list of people? Let's delete that contract. And what we can do is we can make what's called an array. An array is a way of storing a list or a group of some object. So as you're starting to see, the way the syntax works for defining any type of variable is going to be the type of the variable, the visibility of the variable, like public, or if you don't declare it, it gets initialized to internal, and then the name of the variable. It works the same with arrays. So we'll make a people array. The people array is the type. We'll make it public, and we'll call it people. Now if we deploy this contract, we go ahead and see we now have a people array. But if we click this button, you'll see that nothing shows up. And the reason is because it's an empty array to start with, right? We don't have anything inside of it. Now, this type of array that we've created is what's known as a dynamic array. It's a dynamic array because it can change its size. Right now, it's of size 0, and if we added something to it, it's of size 1. You can also create arrays of a fixed size. So if I were to do people 1, public people, this array could only have a maximum of 1 person inside of it. So we're going to work with a dynamic array though, because we want to add an arbitrary number of people into here. So let's go ahead and create a new function called addPerson, where we can add a person to this array. So we'll do function addPerson, string memory name, And I'll talk about this memory keyword in a minute. Uint 256, favorite number. And then we'll make this a public function. And inside, we'll add this person to our array. The way to add a person to your arrays is using the push method. So we're going to push a new people or a new person, and we're going to give it those variables again. So we're going to give it favorite number is this variable that we passed in here. Oops, this needs a bracket. And then we're going to give the name, going to be this underscore name, and then end bracket. Oops. Zoom out again here, just so I can see stuff. This needs a semicolon, and perfect. Now, in that last clip, we saw this little red box pop up. Whenever a little red box like this pops up after you compile, it means you have a compile error. This means that there's something wrong with your Solidity code or your Solidity syntax, and it won't compile and deploy properly. Red is going to be this compile error. Now, we're going to see a bunch of yellow warnings in the future. If you get a little yellow pop-up, these are okay to ignore, but they usually have some helpful tips about something that might be going wrong in your code. So to summarize, if it's red, it's broken. If it's yellow, you might want to check it out, but it could be okay. So we can see we have our new function addPerson, where we pass a string memory name and a uint 256 favorite number. And then we create this people person, this people object here, and then we push it onto our people array. And I'm going to show you another way we can actually create a people person is just by passing favorite number and name. And getting rid of this other bracket by passing favorite number and name. Because we know that the 0th index of people is favorite number, and the first index of people is name. So we can also create a new person by adding it like this. Now let's talk about this memory keyword here. Now in Solidity, there's more or less 2 ways to store information. You can store it in memory or in storage. When you store an object in memory, it actually means that it'll only be stored during execution of the function or of the contract call. If we hold it in storage, that means that that data will persist even after the function executes. A string in Solidity is actually technically not a value type. A string is actually an array of bytes. A variable of type string is actually a special type of array that we can append text to. So because it's technically an object, we have to decide where we want to store it, in memory or in storage. And since we only need this name during the execution, we can have it be string memory name. And then when we create this new people object, we will create a new copy of this name variable into storage. Memory means that after execution, delete this variable, and storage means keep it forever. If this is a little bit confusing for you, just know that for now, when you use a parameter that's going to be a string for one of your functions, you need to call it string memory. So let's go ahead and deploy this contract and see what happens now. Now we have this new function, addPerson. And since we are making a state change here, we can see that this indeed is a orange button instead of being a blue button. So we can add in here a string name. We'll add Patrick, and we'll say his favorite number is 2. Again, right now, if we look at people, we see people 0, there's nothing in here. If we retrieve, there's nothing in here. So we're going to add person Patrick, and now if we hit people of 0, we can see that the person at the 0th index in this people array is going to be string Patrick. If we try at 1, there's nothing in here. Let's add another person. We'll add Becca, and her favorite number will be 24. Let's add her. Now if we hit 1, we see favorite number 24, string name is Becca. And retrieve is still showing up blank because we haven't touched favorite number. Awesome, this is great. We can just keep adding people. However, there is kind of an issue here. What if I'm looking for a person? What if I'm looking to find Becca and find her favorite number in this array? What if I know her name, but I don't know her favorite number? Is there an easy way for me to find that favorite number without having to triage the entire array? There's another data structure called a mapping. So let's create this new data structure. So this data structure is going to be of type mapping. A mapping takes some type of key and spits out whatever variable it's mapped to. So in this case, if we're saying we want to use the name Becca to find her favorite number, we would say the string Becca is going to be mapped to the uint 256 favorite number. And similar to all the other variable declarations, the first part is going to be the typing. So this is going to be a type mapping of string mapped to uint 256. We're going to give this public visibility, and we'll call it name to favorite number, and without adding any other function.